In this section, we're going to continue talking about area and the area underneath a function, but this time we're going to be talking about the area between two functions or between two curves. In order to think about area, we should review the integral and how it relates to area. So remember that the signed area from the function to the x-axis on the interval a, b is given by the definite integral from a to b. And if we draw a picture of this, we have some function here. We'll draw the function so that it goes above and below the x-axis here. On the interval a to b, the signed area is represented by the area from the function to the x-axis. If the function is above the x-axis, then that area is positive. And if it is below the x-axis, we go from the function to the x-axis, that area is negative. While this area is positive. And we could just take all that area, add it up, and we would have the area, the value of the definite integral. Now we learned last chapter that to find the value of this definite integral, we could use the antiderivative, but we're going to be thinking about just area right now and how to deal with that area. Remember that we can estimate this area using a bunch of small rectangles. So let's take a look at a picture of that. We're going to draw the same function here, same bounds, thinking about just estimating this function with rectangles. So I'm going to draw a few rectangles here that's going to estimate the function. We'll use the red rectangles to represent that it's negative area below the x-axis. And we go to the function value at some point. What point we're picking, it could be the left endpoint, the right endpoint, the midpoint, or something in between. But if we add up the area of all of those rectangles, each of those rectangles has a width of delta x and a height of f of x sub I. And if we want to find the area total, we have that the integral from a to b of f of x dx, this area, is approximately equal to adding the area of all of these rectangles, which is base times height, f of x sub I times delta x. And we know that if we take more and more rectangles, we can find that this is exactly equal to the integral. So we have the integral from a to b is equal to the limit as n goes to infinity of this sum. And if we draw those rectangles here, they're very, very, very small rectangles with an itty-bitty width, and there are infinitely many of those rectangles. If we take a look at one of those rectangles, we'll just draw it as skinny as I possibly can with the tools available to me. The width here is dx, and the height here is f of x. So for each x value here, we're going to have some rectangle with a height of dx, and the height is just the function value. So when we're thinking about the integral, we could think about it as a Riemann sum where we're adding up the area of infinitely many rectangles, one for every x value in that interval. The width is infinitely small. That's what this dx represents. An infinitely small value. and f of x is just the height of that function. All right, this is review from chapter 4, but we're going to use this idea throughout chapter 7. So moving on, now we're going to think about the area between two curves. So the area between two functions, f and g, on the interval a to b, where f is the bigger function, is given by the integral of f minus g. We can see this in a picture here. So let's draw two functions. We'll have f is going to be the bigger function, and g is going to be the smaller function. And if I want to find the integral from a to b, I want to find the area between those functions given by that area right there, from a to b. And one way that I can think about this is that I can think about if I am going to be estimating this area with rectangles. Let's draw just one of those rectangles right there. The width of that rectangle is some delta x, and the height of that rectangle is f of x sub I minus g of x sub I, or we're going to think about this commonly as top minus bottom. Okay, we're going to take the value of the big function minus the value of the little function to get the length of that rectangle. Another way to think about this is that we can think about this area as looking at the area under f and subtracting the area under g. So f here, draw f, here's g. So we could think about the area under f. That's given by the integral from a to b f of x dx. And we can think about the area under g. But what we're really doing is we're subtracting those two areas, which gives us the formula that we want. F minus g. Again, if you're thinking about infinitely many rectangles, we're saying that this dx is the width of the rectangle, and the height of the rectangle is f minus g for any x value it's going to be that f minus g right there. We're going to do that for every single rectangle, and this integral sign just means to add up all of those rectangles, like we're doing that for an infinite amount. All right, let's look at a few examples, and we will see some different things that might happen. So the first thing we have is find the area bounded between the function x squared and the function square root of x. And it's going to be important that we draw these functions first. You're going to encounter problems where you're already given the graph of these pictures, but if you're not, it's important to know how these are drawn, and you're expected to know how to draw all of these functions. So let's start with that. X squared and square root of x are both pretty common functions. We're not going to do too much work in here, but we know that x squared is the parabola centered at the origin. And we know square root of x looks like that. And it's good to know what is this point right here. This point is the intersection point, and we can always find the intersection points. And we're going to do that for these problems, just so we have a good idea of what's going on. The intersection points we can find by setting the functions equal to each other. So we could set x squared equal to square root of x and solve for x. In order to do that, we need to square both sides. That'll give us x to the fourth equals x. We can't divide by x, but we can move everything over to one side. Factor out an x, and we're left with x times x cubed minus 1. This time we get x equals 0 and x cubed equals 1, which gives us x equals 1. So our two intersection points correspond to the x values of 0 and 1. We could find the corresponding y values by plugging them into either function. How about f? Give us 0, so that's the point 0, 0. And we do the same thing for x equals 1. Let's plug it into f. We can plug it into g as well. Gives us the point 1, 1. Now you may have found those points regardless, but this gives us a nice way to do it for any function. So this is the point 1, 1 here. And we're thinking about the area bounded between those two functions. We are looking for this area right here. The area bounded between those functions. Now what we're going to do is we're going to think about this with rectangles. So if I want to find this area, I could estimate it with a bunch of itty-bitty rectangles. I'll draw a few of those rectangles right here just to get an idea. We're just going to look at just one of these for some x value in between 0 and 1. This is not the x value 1/2. This is just some x value in between 0 and 1. And we can think about what is the width of that rectangle. The width is going to be dx. And the height of that rectangle is going to be the top function minus the bottom function. In that case, this is going to be the top function is the blue line. That's going to be the square root of x. And the bottom function is going to be that black line, the x squared. So the integral that we have here is going to be, for every x value in between 0 and 1, I'm going to find the area of a little rectangle. The base of that rectangle is dx, or delta x, and the height is going to be square root of x minus x squared. And now I can solve this integral plug in 1, plug in 0. This will give us 2/3 1 to the 3 halves minus 2/3 minus 1/3, or 1/3. And since we're talking about area, we should have a units squared. Up an integral that we are able to solve with the techniques that we learned in the chapter 4. And we're going to find out how to set up that integral by looking at a little rectangle that represents something like a Riemann sum that we can find the value of that integral. Now, you can come up with these formulas like top minus bottom, and you can kind of get these generic formulas, but the more you're understanding what's going on underneath, the more you can tackle more complex problems. And we'll see a more complex problem in this next example here. So find the area bounded between 1 plus x squared and 3 plus x. These two functions are harder to deal with. So we're going to start by trying to graph these functions. Uh, 1 plus x squared is x squared and then moved up 1 unit. Function transformation of 1 unit. So let's graph that function. And the 3 plus x is a line. Y-intercept is the point 0, 3, and the slope is 1. So we could graph that function right there, and we're looking for the area bounded between. So first of all, again, it might help to realize what are the intersection points here. This might be helpful to start as actually the first thing that we do. We're looking for what are these points right here. It's good to be able to graph them. It's good to know exactly what those points are. And we can find that by setting these two functions equal to each other. Move everything to one side will give us x squared minus x minus 2 equals 0. And factoring gives us x minus 2, x plus 1 equals 0, or x equals 2 and negative 1. The corresponding y values, which are also good to find. We plug in 2. Let's plug it into g this time, as that's much easier to deal with. Will give us 5, so that's the point 2, 5. So that means this y value up here is 5, and the other one, negative 1. Plug it into g, gives us a value of 2, so that's the point negative 1, 2. It's good to have that information. We'll see where that comes in the last example that we do in this lecture. So we are trying to find the area bounded between these functions. And it's good to note that when you think about between the two functions, there may be 3 different options of what we have here. The area that's going to work is this area right here. But there are maybe 2 other areas that correspond to between the two functions. Maybe we could think about each of these 2 areas. But both of those areas are going to be infinite. They're just going to keep on getting bigger and bigger as you go out, and they're not bounded. Bounded means finite. So both of those areas are not going to work. We are just considering just the area that is trapped in between those 2 functions. And we are trying to find the area of it. We're going to think about a little rectangle there. So let's draw an arbitrary rectangle. The width of that rectangle is dx or delta x, and the height of that rectangle is going to be from the top function minus the bottom function. In this case, the top function is 3 plus x, and the bottom function is 1 plus x squared. So that's going to give us the integral of 3 plus x minus 1 plus x squared, top function minus bottom function. The width of that rectangle is dx. We're going to find a rectangle for every x value in between negative 1 and 2. Each of those x values are going to correspond to a little rectangle. We drew one of those. We could draw maybe another little rectangle here. Maybe we'll do one more. We need to do that for every single one. So we're just going to draw just one rectangle that represents all of them so we can understand what the formula is going to be. But that's going to give us the bounds of our integral, -1 to 2. And now we have translated this problem into a definite integral that we can solve with methods that we've seen before. So let's do that. This is going to be the integral from -1 to 2. And let's just simplify. Let's distribute that negative. This is going to give us a negative x squared plus x plus 2 dx. The antiderivative is -1/3 x cubed plus 1/2 x squared plus 2x, evaluated from -1 to 2. And we can find this by plugging in the 2. And subtracting off, plugging in the -1. And simplifying, this is going to give us a -8/3 plus 2 plus 4 minus 1/3 plus 1/2 minus 2, which would simplify down to 9/2 units squared. Let's look at this problem just a little bit more. This is definitely the way we're going to do it, but just think about what could have gone wrong in this problem maybe. So let's redraw this function quickly. Here's the 1 plus x squared. Here's the 3 plus x. Let's think about if I did some other things. So let's say that I did instead the integral of 1 plus x squared minus 3 plus x. From -1 to 2. That's flipping the top and the bottom functions, doing that in the wrong order. If you do this, then you should have gotten an answer of -9/2 units squared, which is not correct. This should be positive area, but because you flipped those, you're going to get a negative out from your final answer. Right, so that would be doing bottom minus top, which is not what we want to do. So this is not what we want there. Let's say we also did something like, instead of finding the area bounded between those two functions, we found this area right there. That area would be, this is going to look a little bit funky, but it's going to be all the x values from -infinity to -1. The top function here would be 1 plus x squared. The bottom function would be 3 plus x. But this answer would be infinite. That is an infinite area that we would get out. And that's not what we want to deal with. That's a much different sort of thing that we'll talk about in Calc 2. But at this point, we want to think about just the finite area, the bounded area, trapped in between those two functions. And again, we're thinking about top function, in this case, which is 3 plus x, minus bottom function, this 1 plus x squared. All right, let's move on to a different problem here. Find the area bounded between y equals sine, y equals cosine, x equals pi over 2, and the y-axis. So we need to start by graphing these functions. The first one we have is that we have the y-axis, also known as x equals 0. So this is one of the functions that I'm drawing, x equals 0. The next one I'm going to draw is the function x equals pi over 2. I'll label that right there. That is going to be the x value of pi over 2. And I'm going to be trapped in between those two functions. So I'm not going to consider anything to the left of the y-axis or anything to the right of pi over 2. Now let's draw the more complicated functions, the sine and the cosine. Sine is going to start at the origin, and we're going to finish at pi over 2 comma 1. That's going to be our function sine of x. Cosine is going to start at 0, 1. You're going to finish at pi over 2, 0. There's our function cosine of x. So we're trying to find the area bounded in between those four functions. We need to be trapped in between those two vertical lines. And then we're going to think about the area between those two functions. That's going to be given by this area right here and this area right there. There are two functions to consider, or two areas to consider. And what changes here is that the top and the bottom functions switch. Which makes this problem a little more difficult to do. And what value do they switch at? Well, they switch at whatever x value corresponds to that intersection point. And again, we're going to be considering this idea of intersection points a lot. It's helpful to find the bounds of integral as well as some other information. And to find this, we are going to set sine of x equal to cosine of x. Maybe you could write that as tangent of x is equal to 1 by dividing by cosine on each side. And you can know that that's going to be at x equals pi over 4. So there are two areas to consider. The first area is going to be this one right here, from 0 to pi over 4. So from 0 to pi over 4, we can draw a little rectangle there. And in that case, the width of that rectangle is dx, and the height of that rectangle is going to be cosine minus sine. Because the top function from 0 to pi over 4 is the yellow function there, that cosine, and the bottom function is the sine. But that's going to change for our second integral, which is going to be from pi over 4 to pi over 2. In that case, drawing a little rectangle here, the width is still dx, but the height is now going to be sine minus cosine. What we're doing is we are adding those two integrals together. Both of those integrals are pretty easy to do. We get an answer out. Another way to do this is you can notice that those two areas are going to be equal. So you could write this as maybe 2 times the one of those integrals. If you're not comfortable with that, or you're not sure that those areas are equal, then you should just stick with the two integrals to do by themselves, but it's a shortcut that we might be able to use. The purpose of this example is not about finding the exact value, it's about understanding the difference between top and bottom functions, understanding that they may switch throughout the area that we're talking about, and it's important to really understand the picture, understand what a rectangle is going to look like, and understand what the top and the bottom functions represent. The reason why this chapter can be difficult is because you may want to try to latch on to a formula or a thing that works for every problem, but you will find a lot of problems that do not fit that formula. You need to graph the functions, and for each individual problem, understand what do the rectangles look like and what is top and bottom functions. So let's do one more problem for this chapter, for this section. The area bounded between x equals 1/2 y squared minus 3 and y equals x minus 1. And first off, this function x equals 1/2 y squared minus 3 is a little bit awkward. It's written as x equals instead of y equals. And let's just see what kind of happens for this problem. Maybe the first thing that we want to do is we want to write this as y equals something. So we could do that. Move the 3 over. Multiply by 2. And take the square root. We would have a plus or minus thing there. But that would work. It's going to be y equals plus or minus square root of 2 times x plus 3. And we'll go ahead and graph these functions right now to see what's going on. This function we can graph by taking square root of x. We'll say plus or minus square root of x. And we are going to shift to the left 3 units. And then we are going to have a stretch or compression by a factor of 2. We're not going to worry about that so much. We're going to think about just the right and left movements. So let's redraw these axes real quick. So we're going to start by going to the left 3 units, and we're going to draw positive and negative square root from there. So here is positive square root of 2 times x plus 3. And here is negative square root of 2 times x plus 3. The reason why it's written as x equals at the beginning is because it's kind of 2 different functions when we think about it in terms of y equals. We'll think about the x equals in a little bit later. So then we also have the function y equals x minus 1. That is a line with a y-intercept of -1 and a slope of 1. So let's draw that function real quick. That's going to give us something that looks like this. And it might be really important to know what the intersection points are. And in this case, it's going to be much easier to do that in terms of the x values. So we have x equals 1/2 y squared minus 3, and we have x equals y plus 1 from that y equals x minus 1. Setting those equal to each other, we can solve. Let's multiply by a 2 to get rid of that 1/2. And move everything to one side. And and we get a y minus 4, y plus 2 factorization, y equals 4 and negative 2. That's going to be the y values associated with these two intersection points. And to find the x values, we can just plug into the to either function. So how about x is equal to 4 plus 1? That's going to give us 5. So that's the point 5, comma 4. And x is equal to negative 2 plus 1, negative 1. That's going to be the point negative 1, comma negative 2. All right, and now we have a good detailed picture, and from there we can now think about top and bottom functions. We're going to do that on the next page. So I'm going to redraw this very quickly. So we had our square root of x. We had our two intersection points. Let's draw those first. Negative 1 and negative 2. And 5, comma 4. Think about the line connecting those 2 points. That's y equals x minus 1. Think about the positive square root. It's positive square root of 2 times x plus 3. And the negative square root of 2 times x plus 3. And the area that we're considering is the area bounded by all three of those functions. That area right there. And we need to think about what are the top and bottom functions for this problem. But the issue is that the top and the bottom functions change. And they change at that x value associated with negative 1. So we have two different areas to consider here. The first one is this little area right there. Think about a rectangle for that little area. The width of dx, and the height is going to be the top parabola, or the top square root minus the bottom square root. That's going to give us positive 2 times x plus 3 in square root minus negative square root of 2 times x plus 3 dx. And the bounds for that integral are going to be from negative 3 to negative 1. That's that green area right there. Top is the yellow square root part, the bottom is that blue square root part, and we're going from negative 3 to negative 1. Then we're also going to consider this area, and in that area we think about just a generic rectangle. We have dx is the width, and the height is going to be the top, which is the yellow square root, minus the bottom, which is the line. So that's going to be from negative 1 to 5. So that was that intersection point that we found. In this case, the top function is still that square root. And the bottom function is the line, x minus 1. And we could find that area by doing those two integrals. That's kind of gross with the square root and doing two different integrals. That's what we would have to do. But we're going to do this problem in a much easier, different way, in a different way that has to deal with horizontal rectangles instead of vertical rectangles. Let's take a look at that on the next page here. So this was written as x equals 1/2 y squared minus 3, and thinking about it in that way is useful. So let's think about this function itself just in terms of x, and we're going to think about this as x equals y plus 1 instead of y equals x minus 1. So let's first think about what does x equal y squared look like. That is a horizontal parabola opening to the right. And when you're thinking about this x equals y squared, you can get the 1/2 y squared minus 3 by doing some function transformations. The minus 3 is going to give us a movement to the left 3 units. That's like going down in the x direction, 3 units. And the 1/2 is just a scaling factor. That's going to make this a little bit skinnier. Drawing this problem, drawing these functions, we're going to get the exact same picture that we had before, but our functions are going to be a little bit different. We've already done all the work to graph the functions, but now we can think about our intersection points, -1, -2, and 5, 4. We have our line, which is the same as before, except we're going to write it as x equals y plus 1. And this time for our parabola, we're just going to have one parabola, or one function here. We're going to call that the x equals 1/2 y squared minus 3. And we're only going to have one area to consider. Again, this area right here. And we're going to do that by using not a vertical rectangle, but a horizontal rectangle. In this case, the height of that rectangle is dy. It's a small change in y. It as top minus bottom. If you take your paper and you rotate it 90 degrees, you can think about everything as vertical. You can think about top minus bottom function there, the top being the line, the bottom being the parabola. So we are going to do an integral here. The area of the rectangle is going to be y plus 1 minus 1/2 y squared minus 3. The height of that rectangle is dy. And we're going to have a rectangle for every y value in between -2 and 4. For each y value in there, we're going to have a little rectangle, and we're going to add up all of those rectangles to get the area that we have. So the bounds are going to correspond to the y values instead of the x values. You could think about this instead as from y equals -2 to y equals 4. And in order to do this integral, everything has to be in terms of y instead of x. The reason this is nice is because this integral is much easier to do than the integral that we found on the previous page, which is 2 integrals with square roots involved. That would be a much more difficult integral to do. So this is much quicker, much cleaner. And we can do that by just thinking about horizontal rectangles instead of vertical rectangles. When you're thinking about horizontal rectangles, you need to do right minus left instead of top minus bottom. And you still need to draw a picture. You need to think about your bounds. And again, you need to think about, does the right and left function change? In this case, it does not, and that's why this was such an easy thing to do. With vertical rectangles, the top and bottom functions did change, so we had to think about that as well. For the rest of this chapter, we're going to be considering volumes. We're going to take this idea of this area, and we're going to expand it to finding volumes of different shapes and different surfaces.